So to recap quickly, we were talking about functions. So given a set D called a domain and a set R called a range, function, and you write it like this, f from D to R, f from D to R is an assignment of one range element to each domain element. And then if x is in the domain, then the range element assigned is this, f of x. Right? And you can visualize it kind of like an arrow diagram like this. So, we had another example here. If R is a set of real numbers, so like from calculus and pre-calculus and your high school algebra classes, when you start talking about functions, you start talking about functions defined arithmetically like this, from the real numbers to the real numbers, typically. So like this is a function from the real numbers to the real numbers. F of x equal e to the x is a function from the real numbers to the real numbers. F of x equals cosine x is a function from the real numbers to the real numbers. So all of these kinds of things that you remember are just one specific type of example of function. Oh, this one right here, f of x is log x, is a function from the positive real numbers to the real numbers. So the domain of a function the function has to be defined on the entire domain. So this is only for positive real numbers when you say it like this. Other types of functions we have looked at. Given any domain D, a predicate P of x is a function P from the domain to the range, and the range consists of two things, true and false. So logic valued functions, predicates. All right, so now again, let me reiterate my caveat here from last time that I said. If there's one thing from this class that students inevitably trip up on here and then in the next class, not the next class, but in modern algebra, math 4510 and 4520, if there's one thing that people just don't quite seem to get a lot of the time is functions. Okay, and especially when we start talking about images and pre-images and things like that. But it's critical because they're an important part of mathematics. So please do take some time to remember the definitions that go along with functions and images and pre-images. Okay, given a function f from domain to range, a subset A and a subset A, the image of A under f is written like this, f of capital A. It's the set of all f of x such that x is in A. And that's a subset of the range. So for example, given this function here, if we let x, it's fine. If we let x be the set containing just 1 and 2, so we'll do it in red. So this is x, and then f of x is right here. F of x is just the set containing A. And then f of the entire domain is the set A, B, C. Notice that it's not the whole range, right? Because we're missing D in f of D. And the image of the entire domain of f of from D to R, instead of being written as f of D like this, it is it is often written, not always, as the image of f, the image of the whole function. So another example here, if f from R to R is a function defined arithmetically by f of x is x squared plus 1, then the image of f is the interval from 1 to plus infinity. And the image of the interval from closed interval from negative 1 to 2 is the interval from 1 to 5. So here's a proposition, and we proved this last time. If f is a function from D to R and A is a subset of B is a subset of D, then f of A is a subset of f of B. And we did a proof of that. And that's where we left off last time. All right. Now suppose the following. So, not really an example, but so oftentimes in math we do the following, right? This is a statement, if P then Q, right? If A is a subset of B, then f of A is a subset of B. Right? If A is a subset of B, then f of A is a subset of f of B. So it's an if-then statement, P implies Q. All right, so now often what we do is we look at Q implies P. And what's this called? Given P implies Q, what's Q implies P called? Does anyone know? It's got a name. Starts with C.
The converse.
The converse. The converse. Right, and remember, right, P implies Q, it means that, you have this kind of containment relationship, right? So you can't necessarily reverse it. That would be a double implication, right? So, or other ways to look at it, P implies Q is P naught or Q, and Q implies P is Q naught or P, which, is not the same as this. They're two different things. Right? They're not equivalent to each other. Not the contrapositive is equivalent, but this isn't the contrapositive. So when we prove an if-then statement, an implication, then we often look at the converse and we ask, is the converse true? Or is it not? If not, why? So when we say we're going to look at the converse, we say, conversely, okay, consider a function f from domain to range and A and B that are both subsets of the domain with f of A a subset of f of B. Does this necessarily imply that A is a subset of B? Does it necessarily imply it? Not that it might happen, or it could, not that it could happen. Does it always happen? Right here we're saying if A is a subset of B, then f of A is a subset of f of B, always. Now we're asking, if f of A is a subset of f of B, does it imply that A is a subset of B? Always. Okay? What's the negation of always? Always yes. What is the negation of always yes?
There is a no.
Yeah, sometimes no. Sometimes not. Dr. Salati, do you always teach class in your pajamas? Well, sometimes I don't. I'll leave that up to you to consider whether or not it's true. Right, so the negation of always yes is sometimes no. Okay, so yeah, we're not interested in sometimes yes. We're interested in sometimes no. Okay, so, all right. suppose f of a is a subset of f of b. Doesn't necessarily imply that a is a subset of b. The answer is no. Okay, and how do you show the negation of a universal statement? You have to show the existence of something that goes against the universal statement. The negation of always yes is sometimes no. Well, when no? Well, for example, here, in this instance. No. Consider the following, and it's called a counterexample. Consider the following counterexample. Okay, so a counterexample is the sometimes no for a universal statement. Right? I mean, if I said to you, all horses are brown, how would you prove me wrong?
Showing you a non-brown horse.
Yeah. Show me a horse of a different color. How many do you need to show me?
One.
Just one. That's it. I'm not asking for a good one. You know, I mean, I'm just one. And it can be as cheesy an example as you want. Right? It can be as cheesy an example as you want, unless I, modify my statement to sort of get rid of the cheesy example, and then you can say, you're still wrong. Here's another one. But that's for a later date. Right? I mean, if I said to you, all horses are brown, you're like, no, Dr. Sly, that's not true. Here's a horse, he's white. Right? I said, oh, okay, all horses are brown or white. No, Dr. Slaughter, you're still wrong. Here's a black one. That kind of thing. But we're not going to be doing that. So here is a counterexample. And again, it doesn't have to be a good example. The cheesier, the better, actually. Typically, the cheesier, the better. Now, 1, 2, 3, 4. So let's say A, I mean, you don't even have to try very hard. Let's say A is this set. So A equals 1, 2. And B is equal to this set. 3 and 4. Let's make them overlap a little bit. 1, 2, 3, 3, 4. So A is 1, 2, 3. B is 3, 4. And now all I have to do is define the function such that f of A is a subset of f of B. Or I'm sorry, let's do it the other way around. Say B is 1, 2, 3, and A is 3, 4. So now all I have to do is define things so that f of A is a subset of f of B. Well, that's easy enough to do. So we'll call this x, y, z. All right, so f of 3 is z, f of 4 is z, and then f of 1 and 2 are both x, we'll say. All right, so f of b is equal to what? So b is the set 1, 2, 3. So f of b is what?
X and Z.
X and z. All right, f of a is what?
Just Z.
Just z. All right, so what do we have? How is this a counterexample to f of a subset of f of b implies a is a subset of b? What's the negation of an implication statement? Remember, P implies Q not is the same as P and Q not. Right? So the hypothesis is true, but the conclusion is false. Do I have hypothesis true, conclusion false?
Yeah, even though the function of A is a subset of the function of B, A is outside of B.
F of A is a subset of f of B, but, right, A is not a subset of B. Right? So the implication is false. In this example, that's a counterexample. Not that there's other examples where, it doesn't happen. I mean, there are certainly plenty, but here's a counterexample, right? So we proved over here, that A, a subset of B, implies f of A is a subset of f of B. Right? And down below, that counterexample says that f of A is a subset of f of B, does not imply that A is a subset of B. It does not imply. So let's write that down. Let's write that down here. Therefore, we have established that A subset B implies f of A is a subset of f of B. And f of A subset of f of B does not imply A is a subset of B. Does not imply, does not necessarily imply, something like that. Something of that flavor. All right. Let's consider the following now. So we've been talking about images here. Let's introduce the next concept called a pre-image.
And do you know why baby can't close it?
All right. Definition. Given f from domain D to range R, and x, a subset of the range, okay, the pre-image of x under f is, and it's denoted as follows. It's the set of all little a in A such that f of A is in X. So that's the pre-image of X under F. This is not an inverse function. Okay, given a function f, inverse functions don't necessarily exist. Okay, they usually don't. Okay, only under certain prescribed circumstances do they ever actually exist. Okay, this is a pre-image. What is the pre-image? Notice that, right, f inverse of x is what? What is it? What sort of thing is it? It's an element of the domain, or it's a... What is it?
Is it an element of the range? Or
Well, you
subset of the
start with a
range?
subset of the range. So X is a subset of the range. So what is the pre-image F inverse X? That is a subset of something.
Of the domain?
A subset of the domain. Okay, so a picture would look something like this. Here's your domain. Here's your range, right? And if this is X right here, then the pre-image is everything in the domain. Everything in the domain that goes to X. So all the arrows here go into X. And all the arrows outside here don't go into X. Okay, so that's X here. This is the pre-image of X. Okay. So a little bit of a warning. Okay, F inverse X is not a function. From range to domain. Is not a function from the range to the domain. Sometimes it is, but only under very special circumstances. Okay. It is a function from a certain set to a certain other set. Does anybody see what it is? It's a function from
A subset of the domain to a subset of the range?
yeah. So what is that? It's a function from the power set of the range to the power set of the domain. All right, you take a subset of the range, and it gives you back a subset of the domain, which could be empty, by the way. So, for example, don't think of it as an inverse function. Well, let me not write that down. So, for example, here's a domain, here's a range. 1, 2, 3, 4, 5, 6. And A, B, C, D. We'll say 1 goes to A, 2 goes to A, 3 goes to B, 4 goes to C, 5 goes to A, 6 goes to B. All right, so that's F. So F, the pre-image of, and let's put an element E here. The pre-image of DE is going to be what?
Nothing.
Yeah, being what? It's got to be a set. It's the empty set. Right? The pre-image of just D by itself is still the empty set. The pre-image of, let's say, A and B. The pre-image of A and B is what? So what goes to A and B? Go to A and B.
1, 2, 3, 5, 6.
1, 2, 3, 5, 6. The pre-image of just C by itself.
Four.
Is that right? I mean, yeah, yes and no. It's right, but yet it's not right. What's missing there?
the set of 4?
It's the set containing just 4. Yeah. Preimage of a subset of the range is a subset of the domain, not an element of the domain, a subset, even if it's got one thing in it. Okay? All right, so let's look at the following proposition. So let f be a function from domain to range, and A and B be subsets of the range, not the domain. Okay, prove that A subset of B implies f of A, or no, sorry, f inverse the preimage of A is a subset of the preimage of B. Well, not prove that. It's a proposition. A subset B implies preimage A is a subset of preimage B. Let's prove that. Okay? So, assuming A is a subset of B. Whenever you want to prove an implication statement directly, okay, you have to assume the hypothesis is true, show the conclusion is then forced to be true. Right? When is an implication false? When the hypothesis is true and the conclusion is false. That's the only time a hypothesis is false, or sorry, an implication is false. When the hypothesis is true and the conclusion is false. So, to prove an implication is true, you must assume the hypothesis to be true, and then show that the conclusion is then forced to be true. Therefore, the situation where the hypothesis is true and the conclusion is false doesn't happen. So, that's the direct proof. We also talked about proof by contradiction. Okay, right now we're doing the direct proof. So, assume that A is a subset of B. All right, to show that the preimage of A is a subset of the preimage of B, consider what? How do you show one set as a subset of the other?
That any element in the smaller set
Yeah.
must be in the other set.
Yeah, consider X an element of the preimage of A. By definition, what? By definition, what can you do with that X? What does X do?
It must also be an element of preimage of B.
Not yet. By definition, right, X is in the preimage of A, implies what? Or sorry, not implies. X is in the preimage of A. By definition of the preimage, let's look at the definition. Right? Something is in the I'm using the wrong. I switched letters again. That's fine. So here's X. Oh boy. Let's just change these to A. The preimage of A under F settable X in the domain. Oh, it was supposed to be domain. Such that F of A, F of X is in A. So this is A, and this is preimage A. And f inverse is not a function from the range to the domain. It is actually this. Okay, all right. So given f from the domain to the range, you let A be a subset of the range. The preimage of A under f is f inverse A. It's the set of all domain elements, x, such that f of x is in A. It's the set of all x in the domain, such that f of x is in A. So going back down here, we took x in the preimage of A, so by definition, what can you say about x?
Um, that is just in.
Let's go back, look at the definition again. The preimage of A is the set of all x in the domain, such that f of x is in A. The set of all x in the domain, such that f of x is in A. That's the definition. So down here, we said, consider some x in the preimage of A. So by definition, what can you say about x?
That's an A.
X is not an A, no. It's the set of all x in the domain, such that f of x is in A. All right, so here we picked x in the preimage of A. So by definition, what?
F of x is an A.
F of x is an A. Wait, what did I do? Yeah, right, f of x is in A. What did we assume about A? What did we assume about A?
That is within B.
Right, A is a subset of B. What else do we get about f of x? A is a subset of B, so every element in A is in B. So which element are we talking about in A right now?
F of x.
Yeah. So since A is a subset of B, what? What do we have?
F of x is a subset of B?
Or not subset. F of x is a
Oh, belongs to B?
f of x is an element
It's
of
an element.
B. Yeah, element of belongs to. That's fine. So by definition, what? F of x is in B. So by definition, what can we say about x?
That it's in the preimage of B.
Preimage of B. Please go upstairs. Be quiet, okay? And that's it. So we'll use our end of proof emoji here. So assume that A is a sub. We're trying to show that A implies B, or so A is a subset of B, implies F preimage of A is a subset of preimage of B. So we assume the hypothesis is true. A is a subset of B. To show that preimage A is a subset of preimage B, you consider X in the preimage of A. And what we want is that X is in the preimage of B. And that's what we got. All right, so assuming X is in the preimage of A, by definition, F of X is in A. Because A is a subset of B, any element of A is also in B. But since f of x is in B, by definition, x has got to be in the preimage of B. And that's it. What about the converse now? What about the converse? So with the preimage, what sort of, the sort of analogous statement that failed with images actually works with preimages. Preimages are just sort of more well-behaved in a way than images are. Let's copy that. And A and B be subsets of the range. So preimage of A subset of preimage of B implies A is a subset of B. Proof. Okay, assume that F inverse of A. So again, you need to assume the hypothesis. That's the hypothesis right here. Assume that's true. And now show that this is true. Assume the hypothesis is true. Show that the conclusion is true as well. So assume preimage of A is a subset of the preimage of B. To show that, so just like this previous one, sort of same general blueprint. To show that A is a subset of B, consider what?
That of my table.
That X belongs to A.
Yeah, so consider some X in A. Consider some X in A. We need to show that X is also in B. Well, by definition, the definition's a little trickier here. Because you've got some X in A, what goes on here with X? Consider some X in A. By definition, what happens here?
The X is obtained by an element being put into the function of the preimage of A.
Yes, exactly. How do we say that precisely?
Would it be easier to define this by saying consider the function of X as an element of A? That way we can use X as the element being put into the preimage of A?
Yeah. Yeah, I guess we could do it that way. I want to do it this way, I think, for this one, just to practice with the definition a little bit more explicitly. But what you said is right. There is some y in the preimage of A, such that, or by definition, so by definition, there is some y in the preimage of A such that what?
f of y equals x.
F of y is equal to x. Okay. So what can we now say about y? Y is in the preimage of A.
Which is inside the preimage of B as well.
Because the preimage of A is contained in the preimage of B, y is also in the preimage of B. So we also have because y is in the preimage of B, we now have what? Y is in the preimage of B, so if I
f of y is in B then?
is in B, right? By definition, we now have that x, which is equal to f of y, is an element of B. Y is in the preimage of B. Let me not write it this way. We now have that f of y is an element of B. Right? And then so x, which is equal to f of y, is in B. Let's do it that way. Y is in the preimage of A. Because the preimage of A is a subset of the preimage of B, we also have that y is an element of the preimage of B. But by definition, things in the preimage of B, when you hit them with f, they go into B. So x is in B. X, which is equal to f of y, is in B. And that's it. So the preimage, has a little bit better behavior with regard to, this sort of subset containment than image did. Okay, so we have established the following two facts. So given f from A to B, we have established our domain to range. And A and B subsets of the range, we have proven that A contained in B implies, let's put this on the next page. A contained in B implies the preimage of A is contained in the preimage of B, and the preimage of A contained in the preimage of B implies that A is a subset of B. So this implication and its converse are both true. right? So in propositional logic, we therefore have that P implies Q and Q implies P is true. Right, where P is the proposition A subset of B, and Q is the proposition preimage of A is a subset of preimage of B. So P implies Q and Q implies P. So an implication and its converse are both true. Which means what? What's the more compact propositional logic statement? The double implication. So logical equivalence is often called double implication because it's both implications. P implies Q and Q implies P. Therefore, the double implication, or not that is, but therefore, the double implication, that is, logical equivalence, P if and only if Q is true. P if and only if Q is true. So that's written as follows. Given F from A, or from domain to range, and A and B subsets of the range, A is a subset of B if and only if the preimage of A is a subset of the preimage of B. Okay? So within every statement that says if and only if, there's actually two statements being said. Within every if and only if statement, there's actually two statements. P if and only if Q. When you say P if and only if Q, normally what you mean is that P implies Q and Q implies P. One implies the other, or they're logically equivalent to each other. So a proof of an if and only if statement contains two proofs. The proof of, one direction, one implication, and the proof of the converse implication, which we did. So normally they're not presented as two separate results like that, two separate propositions, but I did it here just to to draw attention to what it is that we're doing here. Let's try another one. If and only if type statement. Well, actually it's 113. Okay, so that's all we have time for